Section 8.3, Rational Functions and Their Graphs. By the end of today's lesson, students are going to be able to identify the properties of rational functions and be able to graph them. A rational function is a function that is written in this form: f of x equals p of x divided by q of x. So that means you could have a polynomial on top of a polynomial. There are two types of rational functions. The first type is a continuous graph, and this means that it has no jumps, breaks, or holes. So if you were to look at a picture of this in a graph, your book shows it like this. It's never going to stop. There's never going to make it jump to anywhere else. It's going to look like that. So a discontinuous graph is going to have a jump, or it's going to have a break, or it's going to have a hole. So if it has a hole, it might look like this. If it has a jump or a break, that would be like where it doesn't cross over your vertical and your horizontal asymptotes. So this would be a discontinuous graph because it jumps from one side to the other side. Points of discontinuity are going to be points where the graph is discontinuous, so where the graph has a hole or where there's a vertical asymptote. And there's two kinds. There's a removable discontinuity and then there's non-removable discontinuities. So an example of a removable discontinuity would be if I gave like x plus 3 times x plus 2 divided by x plus 3. Since there's an x plus 3 on the top and on the bottom, it can be removed from the equation, which means your equation is now x plus 2. So since it's removable, this is considered a hole in your graph because it's taken away. And to find out what the hole is, you set x plus 3 equal to 0, and you get x equals negative 3. You then take the negative 3 and plug it in to the equation that you have left over to find the point. So when I plug in negative 3, I have negative 3 plus 2, which is negative 1. And then the point is negative 3, negative 1, where there's a point of removable discontinuity. Non-removable points of discontinuity would be things that you cannot remove. So if I gave you x plus 5 over x minus 1, neither of those cancel out because it's plus 5 on the top and minus 1 on the bottom, and the discontinuity is only going to come from the denominator, and that's going to be where your vertical asymptote is. So you set it equal to 0, and the vertical asymptote is at positive 1, so there's a non-removable point of discontinuity at x equals 1. Let's look at our first example of finding points of discontinuity. So I give you y equals 1 over x squared minus 16. So you're always going to try to factor this problem. So y equals 1 over x plus 4 and x minus 4. So since nothing cancels out, this is going to be a non-removable point of discontinuity. Set x plus 4 equal to 0. Set x minus 4 equal to 0. So that gives me a non-removable point of discontinuity at x equals negative 4, a non-removable point of discontinuity at positive 4. Now let's find the x-intercept. So to find the x-intercept, you plug in 0 for y. To solve, you would multiply up by that, which is going to give you 0 equals 1, which cannot be true, so there's no x-intercept. So then to find your y-intercept, you're going to plug in 0 for x. So it's going to be 1 over negative 16. So your y-intercept is 0, negative 1/16. So the vertical asymptotes are going to affect my domain. So my domain is going to be from negative infinity to negative 4, and then it's going to jump from negative 4 and it's going to go to positive 4, and then it's going to jump from positive 4 and go to infinity. The y-intercept is going to affect your range. Now, In example number 2, I give you y equals x squared minus 1. So you are going to factor this problem, and that's going to give you y equals x plus 1 times x minus 1. And you cannot factor the denominator. It gives you, it's a plus sign. So looking at this, nothing is going to cancel out. But if you were to set x squared plus 3 equal to 0 to find your vertical asymptote, you're going to get x squared equals negative 3, and then you're going to take the square root of a negative number and it's going to give you imaginary, so there is no vertical asymptote. So this means that there is no points of discontinuity. So since there's no points of discontinuity, it's not going to affect your domain at all. It's going to be all real numbers, which means negative infinity to positive infinity. Last example in the section's about points of discontinuity, y equals x plus 1 divided by x squared plus 3x plus 2. So again, factor first. So that gives me x plus 1 in the top, and then x plus 2 times x plus 1 in the bottom. Since they have x plus 1 in the top and the bottom, that means there is going to be a removable point of discontinuity. So since it's removable, that means it's a whole, so you set x plus 1 equal to 0, and you get x equals negative 1. So then your new equation is 1 over x plus 2, so you take the x minus 1 and you plug it in for x. So that's going to give me 1 over negative 1 plus 2, so that's going to give me 1 over 1, which is 1. So my removable point of discontinuity is negative 1, positive 1. Now, since I still have a denominator, that means I also have a non-removable point of discontinuity. So I take my x plus 2, set it equal to 0, so x equals negative 2. That's where my vertical asymptote is. So your domain is going to be affected by the removable and the non-removable point of discontinuity. So it's going to start from negative infinity, and then negative 2 comes first. And then it goes from negative 2 to negative 1, because remember, domain is only the x values. And then it's going to go from negative 1 to positive infinity. To find the vertical asymptotes in these rational functions, you're still going to factor the denominator, and then you are going to set those factors equal to 0. Now there's 3 different situations to find your horizontal asymptote. The first situation is when your numerator's degree is smaller than your denominator's degree. This is going to make your horizontal asymptote y equals 0. The second scenario is when the numerator's degree is larger than the denominator's degree, and this is going to make no horizontal asymptote. It will become a slant asymptote. When the numerator's degree equals the denominator's degree, you use the leading coefficients to get a divided by b as your horizontal asymptote. Now we're going to do one problem that pulls it all together. So we have y equals x plus 3 divided by x squared minus 6x plus 5. So the first thing you want to do is factor this. So x plus 3 in the top, and then what multiplies to 5 that adds to negative 6. So x minus 5 and x minus 1. So nothing cancels out, so we can go ahead and find our vertical asymptote. Remember, that comes from the denominator, so you set x minus 5 equal to 0, x minus 1 equal to 0. Now we're going to add 5 and get x equals 5, add 1 and x equals 1. Now let's look at the horizontal asymptote. So those are our 3 new scenarios. So the numerator's degree is a degree of 1. The denominator's degree is a degree of 2. So since the denominator's degree is greater than the numerator's degree, it's y equals 0 for your horizontal asymptote. Now let's find the x-intercept. Plug in 0 for y. So 0 equals x plus 3 divided by, and you can either use your factored form or your unfactored form. Since nothing canceled out, it doesn't matter. Okay, so multiply up and you get 0 equals x plus 3. Subtract the 3 and x equals negative 3. So you have negative 3 comma 0 as your x-intercept. Now let's find the y-intercept. Now let's find our y-intercept. Let's plug in 0 for x. And this might be easier in the simplified form, or in the original form, just because you're not then multiplying it. 0 squared minus 6 times 0 plus 5, and that's going to give us 3/5. So our y-intercept is 0 3/5. So I went ahead and graphed your two vertical asymptotes at 5 and at 1, and then here's your horizontal asymptote at y equals 0. Okay, graph the x-intercept, so it's negative 3 comma 0. And then graph the y-intercept at 0 3/5. All right, so now we have 3 sections, so we need to have 2 points to the left of this asymptote, 2 points in the middle, and 2 points on the right-hand side. So let's plug in negative 1. So we have y equals negative 1 plus 3 divided by negative 1 squared minus 6 times negative 1 plus 5. So negative 1 plus 3 gives me 2 on the top. Negative 1 squared is positive 1. Negative 6 times negative 1 is positive 1. And then plus 5 is going to give me 12. And that is going to simplify to 1 6. So our first point is negative 1 1 6. So that's going to be a little lower than 3/5. Okay, 2 points make your branch. Okay, in the middle, if you've noticed, you are negative 3 comma 0. It would help if I drew it in the right spot. Can't erase it. Okay. So, not there. Negative 3, 0. It's right here. Sorry, guys. Alright, so first thing we are going to do is we're probably going to pick 2 values in the middle because it could either be a parabola or it can be a snake. So let's plug in positive 2 and let's plug in positive 4. So when we plug in positive 2, 2 plus 3 over 2 squared minus 6 times 2 plus 5. So that's going to give me 5 on the top. 2 squared is 4. Minus 6 times 2 gives me negative 12. Plus 5 gives me negative 3. So negative 5/3. So it's the point 2, negative 5/3. So that's a little past negative 1. Okay, and let's plug in positive 4. So 4 plus 3 gives me 7 on the top. 4 squared is 16. Minus 6 times 4 is minus 24. Plus 5 also gives me negative 3. So negative 7/3 is going to be a little past 2. Negative 2. So it's the point 4, negative 7/3. So since all of these points are down here in the bottom, it just kind of touches this. It might go up and through it a little bit, and then it comes back down. All right, now to get the right side, we're going to plug in 6 and we're going to plug in 7. So 6 plus 3 gives me 9 on the top. 6 squared minus 6 times 6 plus 5. So that gives me 9/5. So that is almost greater than 2, so, but a little less than it. Okay, now let's plug in 7. Okay, Okay, so 7 plus 3 in the top gives you 10. 7 squared minus 6 times 7 plus 5 is going to give you 12 in the bottom, which is going to simplify to 5, 6. So 5, 6 is a little less than 1. Okay, 2 points, make your branch. And it looks like this. So your parabola in the center can only touch the 3 because I don't have two x-intercepts, so it's just touching there at x equals positive 3. So now let's talk about all of our different characteristics. So our domain. So all of these vertical asymptotes are going to affect our domain. So it's negative infinity to 1, union 1 to 5, and then 5 to infinity. Okay, we're not going to do range just because when we add our slant asymptotes it gets a little crazy. So we're just going to do domain. Now the asymptotic behavior, there's two sets. So as x goes to 1 on the left side. So on the left side of this 1, my graph is going to positive infinity. Then as x goes to 1 on the right side, your graph is going towards negative infinity. So then as x goes to 5 on the left, so as we get closer to 5, on the left side, your graph is down here going towards negative infinity. Okay, and then as x goes to 5 on the right-hand side, f of x is going to, so the right-hand side is going up here towards positive infinity. Okay, now your end behavior is still the same. As x goes to negative infinity, f of x is getting closer to your horizontal asymptote, and then as x goes to positive infinity, f of x is going towards your horizontal asymptote.